Hello everyone, welcome back. Today we're going to be doing the last few subtopics for the chapter forces that have been left. This is going to be the last video for forces, and we're going to start with the turning effect of forces or moment. So whenever a force has a turning effect, it's called the moment of a force. An example we have here is like the stop view for a door. Now we want the door to open about this distance. There's two boys, boy 1 and boy 2, who want to push the door. So boy 1 pushes the door with the force F1 and boy 2 pushes the door with the force F2. Now, to be able to put the door in exactly this position right here, we will notice that the boy who's closer, I mean the boy 1, will need to push the door with the force F1, which is higher than force F2. So force F1 will be bigger than force F2. Now why is this? This is because of the turning effect of forces and the laws it has. So the formula for moment is the force multiplied by perpendicular distance from the pivot. Now what is pivot? Pivot is the point from which the door turns. So this point basically, it is the point where it's fixed to the wall. So that point where it rotates is called the pivot. Now as we can see, the boy 1 is standing closer to the pivot, which means that the distance between the force by boy 1 and the pivot is smaller. This is x, and the distance between the boy 2 and the pivot is larger, y. We can see that y is larger than x. So as we know, the formula for moment is the force multiplied by the perpendicular distance. So if we want to calculate the moment for boy 1, it's going to be x multiplied by f1, and if we want to calculate the moment for boy 2, it's going to be y multiplied by f2. Now as we can see that we want to put the door in this position right here, and this position is equal for both boy 1 and boy 2, so they both need the equal amount of moment. But the problem is that the boy 1 has a different perpendicular distance from the pivot than boy 2. Now how does this affect the force that they need to apply? So for example, the moment needed to put the door from here to here is, for example, 10 Newton meter. We'll see that as the distance, but the perpendicular distance for boy 1 is shorter, he will need to have a bigger force, and the distance is larger for boy 2. This y distance is larger, so he'll need to have a smaller force. As we'll do more examples, this will become much more clearer. So what we need to know for now is that the unit for moment is Newton meters or Nm. Now this is a much more attractive visual, much more understandable, that we have our pivot right here as we've labeled, and we have got two forces F1 and F2. So let us see what is the moment produced by these two forces. We can see that both forces are equal. Both forces are 10 Newton meters, 10 newtons. So let's see the moment by F1. So here we have the force and we have the distance. I'm sorry. Now the force is this and the distance is going to be this whole distance because we're calculating the moment for F1. So 1.5 plus 1.5 is 3, and we get that our moment is 30 Newton meters. While if we calculate the moment for F2, we can see that the force is same, but just because the perpendicular distance is shorter, it's 1.5 as we can see here, the moment calculated is half of F1. Now both the forces are same, but the moment is half, and that's only because of the perpendicular distance. So we will say that F1 has a greater moment than F2. So now let's talk about the principle of moment. When a body is in equilibrium, the sum of clockwise moment is equal to the sum of anti-clockwise moment about the same point. There is no resultant moment on an object in equilibrium. So what does this mean? Let's try to imagine. So for example, this is our pivot and this is our slab or door or whatever you want to call it. The moment exerted by the clockwise direction needs to be equal to the moment in the anti-clockwise direction. So for example, if we have two forces, one of them is acting here and the other is acting here, and this distance is 2 while this distance is 5, and we have this force as 10 newtons. We need, if we want the store to be in equilibrium, we need to have the clockwise moment to be able to be equal to the anti-clockwise moment. So this means that for the clockwise moment, by the way, clockwise is this direction, so we're going to calculate the moment for this force first. So the clockwise moment is going to be 10, which is the force, multiplied by 2, which is the distance from the pivot. We will have our moment as 20 Newton meter. So if the clockwise moment is 20 Newton meters and we want this object to be in equilibrium, we need to have the anti-clockwise moment as 20 Newton meters as well. But for anti-clockwise, we don't have our force, so we need to calculate that. Now we know that the clockwise moment is 20 Newton meters, so we can just equate the equation. So for our equation, we have moment is equal to force multiplied by perpendicular distance. So our moment is 20. We need to know what our force is, and as we can see that the distance from the force to the pivot is 5 meters meters. So we will just take this 5 to the other side, and we can see that our x will be 4. So if our x is 4, meaning that if this force is 4 Newton meters, this door will stay in rest. This door will be in equilibrium. Why? Because the clockwise moment will be equal to the anti-clockwise moment. If this force is greater than 4 newtons, we will see that the door will start going in this direction. This is because the moment of the anti-clockwise moment is higher, and if this force is less than 4 newtons, we will see that the door will come to the clockwise direction because this moment, the clockwise moment will be greater than the anti-clockwise moment. Once we do more questions of moment, this will become much more clear, but I hope that this had like basic understanding in your mind. Okay, so another very important thing that we need to consider while doing the questions for moment is the center of gravity. An object behaves as though its mass is concentrated at one point. This is called center of gravity. So an example we have here is a ruler. This ruler is a meter rule, and we know that its weight is about 10 newtons. But the question is, okay, so where will this 10 newton act from? Will the 10 newton be here? Will the 10 newton be here? Will the 10 newton be here? And the answer is that the 10 newton will act from the center of the scale. So the 50 centimeter mark right here. This is where its weight will act from, and this is called the center of gravity. Okay, so another example we can see is this curve. So for humans to be able to stand, we need to have a center of gravity between our 2 feet. Now, if you try to stand with a wall next to you and you lift this feet up in the air, you'll see that you cannot stand, you cannot balance. This is because once you start lifting your feet up, you'll see that your center of gravity, which acts on the center, will not be between your 2 feet. So as this feet will go up, there will be no feet to like capture the center of gravity, and you'll just fall down. And if you just stand like without anything around you, you stand on your 1 feet. It's something like this. So for example, this is your body, this is your head, and like this is your leg in the air. Maybe, I don't know. I'm sorry for my drawing. And this is your feet. So you will see that your center of gravity will be somewhat so that this is directly above your foot. So this is why you can stand on your one leg. But when you're next to the wall, this is not possible because you can't tilt toward this side and you'll just fall down. So just remember that the center of gravity for a regular shape object is always from the center. So for a sphere, it's going to be here. For a rectangle, it's going to be here. For like a cuboid, it's going to be from the center. Okay, so now what do we do for irregular objects? What are irregular objects, you might think? Well, these are the objects that don't have a defined shape like this. We can't say this is a circle, we can't say this is a sphere, or we can't say this is a cuboid. These are irregular objects. Now we have an example here. This is a irregular cut piece of paper, and now we want to see where the center of mass for this paper will be. What we do is that we make a few holes in the corner of the paper, We put the paper against a wall, and then we take a mass hung by a string, and we put the string in the holes. So like here they put the string in hole A. Now we let this mass go, and it will obviously fall down. We what we do is we make a line for where the string is. So we're going to make a line like this. Then we'll change the hole to C, and we're going to make a line like this. Then maybe we have one more hole here. It might be called D, and when we hang it, we'll see that the line will go right here like this. So we can see that all these lines intersect on one point, this point right here. This point will be the center of gravity for this irregular shaped object. Our last topic is going to be stability. Stability of the object refers to how much an object needs to be tilted before it topples over. So as we can see here, we've got a rectangle, and once it goes beyond a certain point of tilting, it will fall down. Like in A, it's going to fall down, while in B it's not. So what do these factors depend on? To increase the stability, we lower the center of mass of the object and increase the base area. If we have two objects, one of them is this, while the other is this, we can see that object A has a bigger base, so it will be more stable than object B. If the center of mass of object A is lower, while the center of mass of object B is higher, object A is going to be more stable. These two factors determine how stable an object is. So the larger the base area and lower the center of mass. This is why this is why cars have a very low center of mass, so that they don't topple over. Car manufacturers try to make their car's center of mass as low as possible. Now, if the car's center of mass is like somewhere here, over here, the car will be less likely to topple over when it gets into an accident or something. But if the center of mass is much higher up, the car will topple over very easily. So remember, larger base area means more stability, and lower center of mass also means more stability.